In the vast expanse of the cosmos, we encounter forces unseen, energies that permeate the fabric of space and time. One such force is radiation, an ever-present phenomenon emanating from stars, distant galaxies, and even the atoms within our own bodies. To unravel the mysteries of radiation, we turn to ingenious instruments like the Geiger counter, a device that has revolutionized our understanding of the invisible world. The Geiger counter, often called a Geiger counter, is a remarkable invention. It allows us to detect and measure ionizing radiation, the energetic particles and waves that can alter the very structure of matter. This ingenious device, named after its creators Hans Geiger and Walter Müller, has become an indispensable tool in various fields, from nuclear physics to medical imaging. The story of the Geiger counter begins in the early 20th century. In 1908, German physicist Hans Geiger, working under the guidance of Ernest Rutherford, developed an early prototype for detecting alpha particles. Years later, in 1928, Geiger, along with his student Walter Müller, refined the design, creating the practical and efficient Geiger-Müller counter we know today. The Geiger-Müller counter, despite its profound scientific significance, operates on surprisingly simple principles. At its heart lies the Geiger-Müller tube, a sealed chamber filled with a special gas, typically argon or helium. This tube acts as the sensing element, where radiation interacts with matter to produce detectable signals. Inside the tube, a high voltage is maintained between two electrodes, a central wire anode and a surrounding cylindrical cathode. This electric field is crucial for the counter's operation. When ionizing radiation enters the tube, it collides with gas atoms, knocking off electrons and creating ion pairs. These ions are then accelerated by the electric field, triggering a cascade of events. As electrons accelerate towards the anode, they gain enough energy to ionize more gas atoms, creating an avalanche of charged particles. This avalanche, known as a Townsend avalanche, amplifies the initial ionization event, producing a measurable electrical pulse. The pulse is then detected by the counter's electronics. To ensure that each ionization event produces only one pulse, a quenching gas is added to the tube. The quenching gas helps absorb excess energy, preventing the avalanche from becoming self-sustaining. This allows the counter to reset quickly and detect subsequent radiation events. The Geiger-Müller counter is a versatile instrument capable of detecting various types of ionizing radiation, including alpha particles, beta particles, and gamma rays. Each type of radiation interacts differently with matter, and the counter's design can be tailored to optimize its sensitivity to specific radiation types. Alpha particles, consisting of 2 protons and 2 neutrons, are relatively heavy and have a short range in air. To detect alpha particles, a Geiger counter typically has a thin mica window that allows these particles to enter the tube. Beta particles, which are high-energy electrons, are more penetrating than alpha particles and can be detected with thicker windows. Gamma rays, the most energetic form of electromagnetic radiation, are highly penetrating and can easily pass through the walls of a Geiger-Müller tube. While Geiger counters are suitable for detecting gamma rays, they are not as efficient as other detectors, such as scintillation counters for measuring the energy of gamma radiation. Despite its many advantages, the Geiger-Müller counter has limitations. One limitation is its inability to distinguish between different types of radiation based on energy. Geiger counters primarily measure the count rate, or the number of radiation events per unit of time, without providing detailed information about the energy of individual particles. Since its invention, the Geiger-Müller counter has become an indispensable tool in countless scientific, industrial, and medical applications. Its ability to detect and measure ionizing radiation has revolutionized our understanding of the atomic world and has led to profound advancements in various fields. In nuclear medicine, Geiger counters are used to monitor radiation levels and ensure the safe handling of radioactive isotopes used in diagnostic imaging and cancer treatment. Geiger counters play a crucial role in nuclear power plants, where they monitor radiation levels to protect workers and the environment. Geiger counters are also essential tools for geologists and archaeologists, who use them to locate radioactive minerals and date ancient artifacts. In environmental science, Geiger counters are used to monitor background radiation levels and detect radioactive contamination. The Geiger-Müller counter, with its enduring legacy, stands as a testament to human ingenuity and our insatiable thirst for knowledge. It has allowed us to peer into the invisible world of radiation, unraveling its mysteries and harnessing its power for the betterment of humankind. As we continue to explore the cosmos and push the boundaries of scientific understanding, the Geiger counter will undoubtedly remain an essential tool in our quest to comprehend the universe and our place within it.